All right, so today's lesson is polynomial functions. And in this lesson, our goal is to be able to graph a polynomial and identify its characteristics, such as end behaviors, zeros, and their multiplicities, y-intercepts, and symmetry. Also to use the intermediate value theorem, which is used to determine if a zero exists between two x values. So we'll be doing that at the end. So the majority of this lesson is about polynomial functions and their characteristics. All right, so end behaviors are the behaviors of the graph as x approaches positive infinity or negative infinity. These are also called limits, and you are going to see a lot of limits when you take calculus. So we're going to start introducing that limit notation if you haven't seen it already. So the abbreviation LIM represents limit, x arrow negative infinity. So this x with the arrow negative infinity means as x approaches negative infinity, which basically is the left side of your graph. The f of x is your y. So they're saying the limit as x on the left side, what's the y doing? So the y is going to be going to positive infinity if the graph is going up, or it's going to be going to negative infinity if the graph is going down. So the limit is either going to be positive infinity or negative infinity for polynomial functions. As we look at rational functions, it's going to be a little different. So for polynomial functions, your limits on the left and the right are either positive or negative infinity. So this next one, you have x approaching positive infinity, which means the right side of the graph. F of x represents the y values. So what is the limit of y as x approaches positive infinity? So again, with polynomial functions, it's either going to be positive infinity if the right side is going up, or negative infinity if the right side is going down. All right, so a polynomial function is a function in the form of this, where basically a sub n is your leading coefficient and n is the degree of your polynomial. So n is the degree, a sub n is the leading coefficient, and has the following end behaviors. So this is basically a summary of all the different end behaviors that polynomial functions could have. So if the ends of the graph are going in opposite directions, so then your degree is odd. So think odd degree, opposite directions on the right and left side. You could also have a degree that's odd and the opposite things are going in opposite directions, where the right side's going down and the left side's going up. But again, that's so odd, think opposite. If your leading coefficient is positive, then this tells you that the right side goes up. So when the leading coefficient is positive, that automatically tells you the right side of the graph goes up. And then once you know that the right side of the graph goes up, then you know that the opposite, if it's odd, does the same, opposite on the left. If you have an even degreed function, think same on the left. So when thinking of your end behaviors, look first at the leading coefficient. This is my way of thinking, adopted or not, but I always look at the leading coefficient first. If that leading coefficient is positive, then I know the right side of going up. Then I look at the degree to tell me if the left side is doing the opposite or if the left side is doing the same. That's kind of my method of thinking through the process. All right, as far as describing them, so if the right side is going up, then you would say the limit as x approaches infinity, f of x equals infinity. So the limit of the function on the right side is positive infinity. It would also be, well, on the left side, let's go back to here. So then the limit as x approaches negative infinity of the function would equal negative infinity because it's going down on the left. If your leading coefficient is positive, you know the right side goes up. If the degree is even, then the left side is going to be doing the same. So the limit as x approaches positive infinity of the function, if you have a positive leading coefficient, is going to positive infinity because the right side goes up. And then on the left side, the limit as x approaches negative infinity is also going to positive infinity because the left side is also going up. So these are going to be the same. If your leading coefficient is negative, so your leading coefficient is negative, that tells you that the right side of the graph goes down. Whether the degree is even or odd, if the leading coefficient is negative, that tells you the right side goes down. So then the limit as x approaches positive infinity, so that's the right side of f of x, so the limit of the function as x approaches positive infinity will be negative infinity. So again, this means the right side goes down. And that always happens when your leading coefficient is negative. So the limit as x approaches positive infinity of the function f of x will equal negative infinity, is how you write that limit for these polynomial functions. On the left side, it's either going to be the same or opposite. So if your degree is odd, then the left side will be doing the opposite. So the limit as x approaches negative infinity means the left side, the function y, or the function f of x, is going to positive infinity if the degree is odd and your leading coefficient is negative. Otherwise, if your degree is even, they're going to be doing the same thing on the left. So the limit as x approaches negative infinity, which means the left side, the function f of x, or your y values, are going down to negative infinity, just like on the right side. So the right and left side are both going to negative infinity when your degree is even. When your degree is odd, the opposite happens on the left side. All right, let me make that a little smaller so you can see it all. Okay, example 2. So we're going to graph the function and identify all of its characteristics. So let's start with our end behaviors. So your leading coefficient, or LC, equals -1. So that tells me that the right side of the graph goes down. So that's what that leading coefficient tells me. When you're describing end behaviors, you usually describe the left first and then the right. So I would say the limit as x approaches negative infinity, f of x equals blank. And then the limit as x approaches positive infinity of the function f of x equals blank. Well, since your leading coefficient is negative, I know the right side is going to go down. So that's a limit on the right is negative infinity. Since my degree equals 4, and that's even means same. So that left side is going to be doing the same thing. It's going to be going down as well. All right, so that's the end behaviors. But we need some points to graph before we can do these end behaviors. So that's where we find our zeros. To find your zeros, set your function equal to 0 and solve. Use a different color. So if I take my function negative x to the 4th plus 6x to the 3rd minus 9x squared, set it equal to 0. I'm going to factor to solve. I'm going to factor out a negative x squared, which then gives me x squared minus 6x plus 9. And then that will factor into x minus 3 times x minus 3 with a negative x squared out front. If I factor this down into linear factors, just to emphasize all the factors, I would have x times x minus 3 times x minus 3. And the reason why I want to do that is to describe the multiplicities. So if you have two factors of x, both of these factors would have a solution of 0. Since there are two factors that have a solution of 0, you would say it has a multiplicity of 2, which affects your graph. That means it's going to touch and turn around at that point. So when you have a multiplicity of 2, or an even multiplicity, it touches and turns around. Or another term, bounces. If you have two factors of x minus 3, then you have two solutions of 3. So again, we have a multiplicity of 2. Even multiplicity, so it's going to touch or turn around at those points. So I can put a couple points now on my graph. The one x-intercept is at 0. The other x-intercept is at 3. The other thing that I can graph is my end behaviors. So I know that the right side has to be going down and the left side has to be going down. So I can sketch the right side going down and the left side going down. Then I use this notion that its multiplicity is 2, so it's going to touch and turn around or bounces at these points. So it's not going to cross the x-axis. If it was an odd multiplicity, it would cross the x-axis, but even multiplicity, it touches and turns around. Now I could get a little bit more accurate of points in my graph if I plug in 1 and 2 into my function, but it's really not necessary. I'm just going to kind of sketch this. So it's going to have to go down and then come back up to hit those points. All right, so but again, if you wanted a little bit more accurate graph, you can put it in your graphing calculator, or you can substitute f of 1 into the function and f of 2 into the function. Actually, let me go ahead and do that. So if I put 1 into the function, again, I would probably just plug this in the calculator. I would get negative 4. So the point 1, negative 4 is on the graph. If I put 2 into the function for x, I would also get negative 4. So the graph would go down and then back up and then hit that. If you don't get that precise or accurate in your graphs, that's okay, as long as you have these end behaviors and the multiplicities correct on there. So the zeros are the points 0, 0 and 3, 0. All right, so your y-intercept, again, you can always find a y-intercept by substituting 0 in for x. But if you look at your graph, you've already got the point 0, 0 on there, so your y-intercept is 0, 0. Symmetry. So for this is basically asking if it's even, odd, or neither. So by looking at the graph, is it symmetrical about the y-axis? No, it is not. Is it symmetrical about the origin? No, it is not. So it's going to be neither. You could also substitute negative x in the place of x. So if you were to take f of negative x, substitute it in for each of these x's, when you have something to an even power, it's going to become positive. But if you have something to an odd power, if you have a negative x to odd power, it becomes negative. So this sign would stay the same. This sign would switch. This one would stay the same. So if you have two terms that are the same as the original, but the one is opposite, also that shows that it is neither. So there's no symmetry here. It's not even or odd. All right, so that's that example. So some miscellaneous information that you need to know about polynomial functions. The number of turning points, or local maxes and mins, is at most one less than the degree of the polynomial. So if I apply that, if you look at the degree of your polynomial, it is 4. How many turning points does it have? 1, 2, 3. So 3 turning points when the degree is 4. So 1 less than what the degree is. If you think of a parabola or quadratic function has a degree of 2, but there's only 1 turning point. A linear has a degree of 1, but there's no turning points. So that's where that rule comes in. A polynomial has at most n zeros, where n is the degree of the polynomial. So if the degree is 4, then there should be 4 zeros, including multiplicities. The next one, the graph of a polynomial function is smooth and continuous. It contains only rounded curves, no sharp corners, no breaks, and it can be drawn without lifting your pencil from the rectangular coordinate system. So basically, that means it's continuous. The graph of f of x flattens out at the x-intercepts or zeros as its multiplicities increase. So I'm going to show you what that looks like. So if you have a quadratic function, so if f of x equals x squared, it would be a parabola that looks like this. So it's got a curve at the bottom. But if you have f of x equals x to the fourth, it would look very similar to this, but it would be a little bit more flat at the bottom and then a little bit steeper on the sides. So they look very similar, but a little bit flatter and a little bit more steeper on the sides if it's x to the fourth. If you have a function that has an x to the third, the parent cubic kind of looks like a half of a parabola going up and a half a parabola going down. If you have a function that's x to the fifth or a fifth degree, at its turning point, it's again going to just be a little bit flatter around that turning point and then a little bit steeper on the sides. So pay attention to those multiplicities. If it's a multiplicity of 4, then at the x-intercept, make it a little bit flatter when it bounces. If you have a multiplicity of 5, it should be a little flatter as it zigzags through the x-intercept. All right, and then the last concept is this intermediate value theorem, which you're going to see again in other math classes possibly. If a polynomial function changes from positive to negative within an interval, then there must be a 0 between the endpoints of the interval. So basically, if you substitute a number a into the function and you get a value that's less than 0, so you get a negative number, Then you substitute b, which is the other end of the interval. So the interval is going to be between two numbers, a and b. So when you substitute a and b into the function, if one of the outcomes is negative and the other outcome is positive, then that means that fulfills this intermediate value theorem. Then there is at least one value of c between a and b for which f of c equals 0. So there has to be a 0 or an x-intercept in between those two values of a and b. So here we go, applying the intermediate value theorem. So use the intermediate value theorem to prove that f of x has a 0 in the interval -2 to -1, including. So your a then would equal -2, your b would equal 1. Substitute -2 into the function. Simplify that, so we get -8, -8, -6. So we get negative 22. So f of -2 is negative. So this f of a is less than 0. So that fulfills the first part of our function or theorem. If we substitute 1 into the function, and we simplify, we get 1 minus 2 plus 3, which ends up equaling 2. So f of 1 equals 2. So that fulfills the second part of the theorem, that f of b is greater than 0. So this is positive. Then that tells us, so since f of -2 was less than 0 and f of 1 is greater than 0, there must be a point or there must be at least one value c where f of c equals 0, which basically means it crosses the x-axis somewhere between the x value of -2 or somewhere between the interval -2 to 1. So that is your intermediate value theorem, and that concludes our lesson. So I almost forgot. When you see polynomials that are in factored form, like these two examples here, and you're trying to figure out what the leading coefficient and degree are, in math, my math lab, it's going to tell you to multiply everything out. You do not need to multiply everything out. So let me show you how to shortcut that. So basically, you've got your -5 that's in front, your x minus 1 to the third power, which basically means you have 3 x minus 1s, and then this x squared minus 7. If you just take whatever is out front, if there's a monomial out front, take that monomial that's out front, the first term in each of these factors, and multiply that together, that will tell you that the leading coefficient is going to be -5, and the degree x, and then if you multiply the x's, 1, 2, 3, 4, 5, you have x to the 5th power. So, and then the rest of the terms really don't matter when it comes to your end behaviors. So your leading coefficient then is -5, and your degree is 5. So then the leading coefficient tells you it's going to go down on the right. Your degree, being odd, tells you it's going to go up on the left. And there'll be some other stuff in between that we really don't care about as far as the end behaviors go. All right, so that's one quick example. And then I have this second example over here that You don't necessarily have to write out all three binomials. So if you take this monomial that's out front, I take this first term to this power and the first term here. That will tell me that my leading term is going to be 4x to the third times x to the third times 2x plus whatever else. We don't care. So if we multiply all this together, you get 6x to the eighth. So now our leading coefficient is positive 6. Our degree is 8. And that tells me, since my leading coefficient is positive, I know the right side of my graph is going to go up. Since my degree is even, the left side will be doing the same. And there'll be some other stuff that goes on in between that we really don't care about. But the right side is increasing. The left side is also increasing.